Okay, so in part A of this video, we showed that the flux of the curl of f across S was negative 4 pi, where S here was the upper half of the sphere. So in this video, we're going to need to show that the line integral around the boundary of f is equal to negative 4 pi. So the boundary is here. And from the first video, we showed that r theta cross r phi was equal to this, and where phi goes from 0 to pi over 2, theta goes from 0 to 2 pi. So the negative 4 in front means that it's going to be pointing inward. So this r theta cross r phi is our n, or normal vector. So it's going to be pointing in to the sphere. So we have to figure out the correct orientation to integrate this guy. So let's figure out the orientation. So again, imagine this is you. I've marked your left hand black. So you need to stand on the boundary and turn yourself so your head's in the direction of normal vectors. So say here, you're on the boundary. And when you walk around the boundary, the normal vectors need to be on your left. So again, the black hand's denoting the left side. So when you walk around, it would have to be this way. That would be the positive orientation relative to these normal vectors here. So if I went that way, then your right hand would be pointing towards the normal vectors. So here, the left hand's pointing towards the normal vectors. So I'm going around that way. So that's the positive orientation going this way. Okay, so I've drawn in the positive orientation here relative to this normal vector. So now let's parameterize this boundary. So let's make an observation. So if the pen is denoting a point on the sphere, say here, and this pen up here is the z-axis, this would be the phi angle, this angle over here. So it'd be 0 would be there on the z-axis. Pi over 2 would put you on the xy plane down here. So pretty much if you choose phi to be pi over 2, that would put you down here. So I can choose pi over 2 in my parameterization up here for S, and that should parameterize the boundary here. So let's do that. So again, I'm letting phi be pi over 2, and let's call theta up in our R up here t. So put that in, put those substitutions into my R theta phi up there, and I'm going to call the new guy R1 of t. So it'd be 2 sine pi over 2 because they got a phi there. Then cosine theta, then 2 sine pi over 2 sine theta, cosine pi over 2. And now the sine of pi over 2 is 1, so that's 1, that's 1, and that's 0. So this becomes then, so simplifying, we get R1 of t then is 2 cosine theta, 2 sine theta, 0. So this will parameterize the boundary, but it may not be in the correct orientation, so we need to check that now. So to check that, let's stick in 2 points. So first I'll put in 0 for my t, and cosine of 0 is 1, so this will be 2, and sine of 0 is 0, so it'll be 2, 0, 0. And let's stick in next pi over 2 for t. So I put pi over 2 in there, so the cosine of pi over 2 is 0, so this will be 0, sine of pi over 2 is 1, 2, 0. And let's draw a little circle now and take a look at the orientation. So looking at R1 of 0 would put you here, R1 of pi over 2 would put you here. So it's going around the circle in the counterclockwise direction. But actually up here we want it to go around in the clockwise direction, so our orientation is wrong. So we can just put a minus sign in front of our line integral, and that will compensate for it. So we'll do that at the end. Or we'll do that, you'll see. So let's keep going. So let me erase a few things here. So summarizing, we have our R1 up here. So be 2 cosine t, 2 sine t, 0. And the t goes from 0 to 2 pi since you're going around the whole circle of the boundary. And that's my f function. So we're doing the integral, line integral over the boundary of our f function. So we need to reverse the orientation, so I just stick a minus sign in front here. Okay, so let's work on this now. Let's do R1 prime. So there's my R up here, so let's do R1 prime. So doing my R1 prime, derivative of cosine be minus sine, so it'll be minus 2 sine ti, derivative of sines cosine to be 2 cosine tj, and that 0 should just be 0k. Okay, now let's do my my f of R1, so let's work this out here. So it'll be then 0 to 2 pi. So that'll be I plus xj, but x now is 2 cosine, so it'll be plus 2 cosine j plus y times z. But notice here z is 0, so y times 0 will be 0, so it'll just be 0k. This guy dot it with R1 prime. So I'll be dotting these then, so it'll be negative 2 sine t times 1, 2 cosine t times 2 cosine t, and 0 times 0. So let me write that over here. So doing that, so it'll be negative 2 sine times 1, so it'll be negative 2 sine here. That'll be 2 cosine t times 2 cosine t, so 4 cosine t squared. So we have to integrate this now. So to integrate the cosine square, we're going to have to make a double angle substitution here. So I'll make this double angle substitution for the cosine squared. When I do that, this will cross off and this will make a 2 here. So then it's going to be 2 plus 2 cosine 2t. So let me write out the result over here. So I get this then. Okay, so now let's start integrating these things. So we're going to have to integrate the sine, the 2, and the cosine of 2t. Let me do it over here. So integrating, I get this. So the integral of sine, negative sine would be a cosine here. Integral of 2 would be 2t. When you integrate cosine of 2t, I'm basically using this formula. You can easily show using the chain rule how it works out. So the integral of cosine of kt will be sine kt over k. So here the k is 2, so it'll be just this. Okay, and let's evaluate now at 2 pi and 0. So putting in 2 pi in place of t, I'm putting in 0. So cosine of 2 pi is 1, cosine of 0 is 1, so this part is 0. This part is going to be 4 pi here. This will be sine of 4 pi, which is 0, sine of 0, which is 0, so this part 0. So then you'll have to have a minus 4 pi as our answer. Our answer then will be minus 4 pi, which is the same as the answer we got from part A. So we showed that the line integral equals the surface integral. So line integral over the f function equals the surface integral over the curl. So we verified Stokes' theorem, so we're done.